Hello, everyone, and welcome to online lecture 4. So first, I just want to share the reading with you for next time. For next time, chapter 10, quasi-experimental design, that's what we'll be talking about. Now, today we're going to talk about the fundamentals of design. Okay, so we're going to really talk about the overall notions of design. Now, I know we already talked about one kind of design, the randomized clinical trial. Right? So that's a good example of what we're talking about today. But today we're going to go a little bit deeper into the notions of design, talk about them theoretically, and then go into a few other examples. Okay. So research design is the glue that holds the pieces of the research project together. For example, the sample, the measures, the treatments or programs, and the method of assignment. So we're going to be dealing with this notion of causality quite a bit. So let's just kind of understand what we're talking about here. So when we talk about causal, we're talking about a cause-effect question, hypothesis, or relationship. And if it's causal, it leads to an outcome. It makes an outcome happen. So that's different from just being associated or just being related. It actually A produces B. Okay, so for example, when you evaluate whether your treatment or program causes an outcome to occur, you are examining a causal relationship. Now, in order to actually show causality, you have to have temporal precedence, which means your cause has to happen before your effect. Cause has to happen before your effect. Covariation of the cause and effect, which means when the cause happens, the effect happens. And equally as important, when the cause does not happen, the effect does not happen. That's a toughie. And if that wasn't enough, you have to have no plausible alternatives. No plausible alternative explanations. Okay, so that's really hard to show because, as you imagine, you could almost always come up with a plausible alternative, especially in our field. Okay. So what's the third variable problem? Well, an unobserved variable that accounts for a correlation between two variables. And we've talked about this third variable problem before. And this basically is showing that correlation does not equal causation, because if it's just something else that's accounting for it, well, then that's not it. So for example, let's say we have one therapist administering cognitive behavioral therapy and another therapist administering psychodynamic psychotherapy. Okay. And it turns out that the one person who's administering the cognitive behavioral therapy, there's always better results, and et cetera, et cetera. But then, is it the cognitive behavioral therapy, or is it the unobserved variable of the therapist, him or herself? Is it the person maybe that's making the difference? In other words, if we gave that person now the task of doing a different kind of therapy, would that person still be as successful a therapist? Would the outcome still be just as good? So we don't know, right? That's an unobserved variable that might account for that association that we're seeing. Okay. So from McWick Labs, we bring you not only the control group, but the out of control group. Okay. So now let's switch gears a little bit and talk about internal validity. Now I'm only switching gears just a little bit. And the reason I say that is because internal validity has a lot to do with causation. The higher your internal validity, the more likely you are going to be able to show that A causes B. Okay. So in this particular example, we have a program, we have whatever we're doing, our our manipulated IV, and we have our observation, what we're seeing, and between them we have the cause that we're trying to prove, but then look at all these other alternative causes that we have to account for. Okay. So let's talk about some threats to internal validity. And we're going to talk about each of these in turn. So we're going to talk about single group threats, multi-group threats, and social interaction threats. So let's start with single group threats. And we're going to talk about each of these in turn. Okay. So this occurs in single group post-test or pre-test post-test designs. And we'll talk more about what we mean by that a little bit later, okay? So history. Actually, let's talk about them in turn here. History, what is a history threat? A threat to internal validity that occurs when some historical event affects your study outcome. So in other words, let's say that you are trying to show that cognitive behavioral therapy is very effective for panic disorder. And you have one group that's getting cognitive behavioral therapy, another group that's getting an alternative form of treatment. And right in the middle of your program, some very, very famous person gets on TV and says, and well-liked person, gets on TV and says, by the way, I've always had panic disorder and I use cognitive behavioral therapy and it has made all the difference. I'm way better for it. That would be a threat of history to your internal validity. Okay. Maturation. A result of natural maturation that occurs between pre and post-test measurement. So that could just mean what you think of with maturation as sort of, time has passed, those sort of things. But it could be any change that happens between pre and post test. Okay. All right. Testing threat. This is when the pre-test affects how the participants do on the post-test. So sometimes, as you know, participants want to please the experimenter, right? So if they did a certain way on the pretest, they might want to show they've gotten better or believe they've gotten better, and then respond differently on the post-test, let's say of a BAI, for lack of a better measure, Beck Anxiety Inventory, and they might perform differently. Okay, just because of the nature of the test. Another great example of this would be, let's say you're using some sort of IQ or cognitive measure, and then the second time around, they might remember how they did the first time, or they might remember some of the questions and be able to perform better. Okay. Instrumentation. A threat to internal validity that arises when the instruments used on the post-test and the pre-test differ. Okay, so we know we try to avoid that at all costs, but sometimes it happens that post-test and pre-test measures don't match up for some reason, or there's some issue with the instrument itself. Sometimes, for all the best reasons in the world, people will add a measure at post-test, like, oh, I really wish I had captured this at pre-test. Well, I'll just add it at post-test. I mean, if you do that, and you don't do it at the end, it could impact how they're responding on other measures, right? Okay. Mortality, this is often called attrition as well, and it occurs because a significant number of participants drop out. So that could be due to mortality, or it could just be due that they drop out because they drop out. Okay. They don't want to be a part of your studying anymore. They can't be a part for logistical reasons. Any number of things can happen. Okay, next one is regression to the mean. And basically this is a statistical phenomenon. And it causes the groups' average performance on one measure to regress toward or appear closer to the mean of that measure more than anticipated or predicted. In other words, when you go from pre-test to post-test, the real far out outliers tend to kind of condense in. Okay, so this can occur whenever you have a non-random sample from a population and the two measures are imperfectly correlated. And it's just a weird statistical phenomenon. We'll just leave that one at that it can just happen that way. So at post-test, things move closer to the average. Okay. Okay. So one way to deal with these single group threats is to add a second group known as a control group. But if you add a control group, you need to address the multi-group threats to internal validity. Okay. And the big multi-group threat to internal validity is that the groups were not comparable before the study. In other words, they're not comparable at pretest. Now, this may be an issue that you've dealt with or you've had some conversations about. So, for example, if you're doing a pretest, post-test with a program in the middle, some kind of treatment in the middle, sometimes what people will do in research literature is say, hey, I checked everybody's age and starting scores at pretest just to make sure across the groups that they were the same, right? That's what they try to do, to try and show the groups are as similar as possible. Now, as we know, random assignment can really help our groups be similar. Sometimes it doesn't work out that way though, right? Sometimes just you get luck of the draw and one group is quite different from the other, even though you randomly assign them. Okay. So there's also something known as selection bias. And you see that we can attach selection to each of these, to most of these different threats we've already talked about, to history, to maturation, to testing, to instrumentation, to mortality, and to regression. So really all the ones we've talked about so far. Okay. Now, the only big difference, and I'll go through these, but basically it's that the history threat, for example, would happen differently to the control than the experimental group. Okay, so let's go back to our initial history example. And I said, you're treating some people with cognitive behavioral therapy. Let's forget about that other group. You're treating some people with cognitive behavioral therapy. Someone ultra famous, ultra likable comes on TV and says that, yep, yeah, panic disorder, I had it, and cognitive behavioral therapy was wonderful. It made all the difference in the world to me. And then you do your post-test, and maybe people are influenced by the cognitive behavioral therapy, or maybe they're influenced by hearing this famous person say that it was effective for them. Now, if that happens with the cognitive behavioral therapy group, but not with your psychodynamic group, that's a selection history threat. Okay, so the plain history threat, just pretend you have one group, and selection history is if you have two groups and it happens differently. Similarly, selection maturation would be if one group experiences maturation at a different rate or in a different way than another group, experimental versus control. With testing, selection testing, maybe the test impacts one group differently than another. Okay. And instrumentation, this is a tough one. This is why it's so important to give both control and experimental groups your same instrument at both pre-test and post-test, because if you change it up for one group and not another, you can have that selection instrumentation threat. Dropout rates, if dropout rates are differential between your two groups. So we might have talked through this example before, but let's talk it through again. Let's say for one group, you're doing this time a weight loss program. For one group, they take a pill. For the other group, they have to do a strict diet and heavy exercise over the course of 2 months. You're just going to look over 2 months. Okay. So which group do you think might have more dropout? Diet and exercise, right? That's a lot more challenging than taking a pill every day. So that's more likely to have the dropout. And then finally, our selection regression threat. That can happen actually if there are different rates of regression to the mean in the two groups. Okay. All right. Okay. So when you do not use randomization to assign your groups, you have a quasi-experimental design, and quasi-experimental designs have weaker internal validity. And what does weaker internal validity turn into? Weaker ability to determine cause and effect. So again, random assignment to groups is a really critical piece of an experimental design. Okay. Now, I do want to make sure we remember the difference between random selection and random assignment. Now, random selection is what we were talking about last time with sampling, right? How do you obtain your sample from the population? After that comes random assignment or assignment. Once you have your sample, how are you going to split this sample into your groups, experimental, control, or what have you? Okay. Oh, sorry, I went backwards. Okay. So now let's talk through some social interaction threats. Excuse me. The first one is diffusion or imitation of treatment. The next one is compensatory rivalry, then resentful demoralization, and then compensatory equalization of treatment. So let's talk about each of these in turn. Okay. So diffusion or imitation of treatment, what's that about? It's a social threat to internal validity that occurs because a comparison group learns about the program either directly or indirectly from program group participants. Okay, so you're giving one group cognitive behavioral therapy. Maybe the other group is a waitlist control, right? So they're waiting on their treatment. And they learn what the program group is getting and they seek it out themselves, perhaps. Okay. All right. Compensatory rivalry. Now, this one happens when one group knows the program another group is getting, and because of that, develops a competitive attitude with the other group. So still, we're learning about what the other group is getting, but this time we're just talking about feelings of a rivalry in response. Resentful demoralization. This one, the comparison group knows what the program group is getting, and instead of developing a rivalry, control group members become discouraged or angry and give up. And finally, compensatory equalization of treatment. This is bad news on the researcher's part. I guess all of these in some ways are bad news on the researcher's part. But this one is a social threat to internal validity that occurs when the control group is given a program or treatment, usually by a well-meaning third party, designed to make up for or compensate for the treatment that the program usually gets, that the program group gets. Okay. So in other words, someone finds out that this group is getting cognitive behavioral therapy for this and decides to go ahead and provide that to the control group participants. So they've equalized the experiment, and now how is the researcher going to be able to determine what the what the effect actually was. Okay, all right. So how can you rule out threats to internal validity? Well, you can do it by argument. Sometimes you just know the literature and you know what's supported and what isn't. You can do it through measurement or observation. You can do it by analysis through a main effect or covariance analysis, or you can do it by preventative action. Okay. So we'll talk about each of those in turn. We'll get to those. There are 4 elements to any research design: time, treatments or programs, measurements or observations, and groups or individuals. Okay. Actually, let's go back for a moment. We'll get to these again, but I do want to actually just make sure you understand the basics of them right now. By measurement or observation, basically what that means is that you can actually observe what's going on that can actually threaten the internal validity and then try to take that into account. By analysis, you can do it by main effect or covariance analysis. The most typical way is to either block it with a main effect, and we will talk about blocking later, or to add it in as a covariate. Okay. And sometimes you can take preventative action to, like, for example, try to prevent some of these items from happening by not adding an instrument at the to your already fixed survey and making it different across experimental control, or making it different between pre-test and post-test. Okay. So we talked about this. So now I want to get into a little bit about design notation. Okay. So I know this kind of looks like a football thing, but it's not. But we do have a lot of X's and O's and R's, and we'll see some N's later. So let's look at this. Okay, so this is time. The R's indicate that your groups are randomly assigned. Okay, so this is one group. This is another group. So we have 2 groups that are randomly assigned. We measure them at pretest. This group gets the treatment. We measure both groups at post-test. So again, each line represents a group. R's represent random assignment. O is an observation. X is the treatment. And as you can see here, we have pretest, treatment just for this group, and post-test. You can also use subscripts to indicate subsets of measures. So here we give O1, just O1 at pretest, and we give O1 and O2 at post-test. Again, not horrible, as long as we give 2 after 1 at post-test. Okay, we like them. I guess sometimes you just really can't give measure 2 at the first stage, but if you could at all, I would have preferred that. Okay. So now let's talk about some designs. Is random assignment used? If yes, it's a randomized or true experiment. If no, is there a control group or multiple measures? If yes, it's a quasi-experiment. If no, it's a non-experiment. Okay. So let's talk about some notational examples. Post-test only randomized experiment. We randomize, give one group the treatment, and observe. Notice there's no pretest here. That's why it's called post-test only randomized experiment. Okay. Here, we're not going to randomize. Here's those N's I promised. We have an observation, treatment, observation. So this could be a very nice experiment, except it's not because we don't have equivalent groups. Okay. This could be due to any number of reasons. Now, sometimes we can't randomize our groups, right? Sometimes it's not within our ability. If we want to know about about age, if age is our variable, our IV, or gender is our IV, well, we can assign people to different genders. We can assign people to different ages. So sometimes we wind up with this quasi experiment here. And then in this example, we only have one group. They were given the program, the treatment, what have you, and then they were observed. So how can we expand on some basic designs? Well, we can expand across time, across programs, across observations, or across groups. And once again, here's our classic pre-test, post-test control group design, similar to what we saw on the previous page, but now we have R's instead of N's, which is nicer, right? So this is an actual experiment here. We randomize our groups, we observe, we give a treatment to one group, and we observe again. Classic pre-test, post-test control group design. So experiments have the strongest internal validity. Why? Due to random assignment to a group. That's what we've been talking about. So we might have flipped a coin, we might have used a random number generator, whatever we did, we found some way of randomly putting people into the different groups. Okay. So who came up with these origins, with this notion of experimental design, that sort of thing? I'm not a big history buff, but a few of these are interesting. So Sir Ronald Fisher, who you know from the t-test and the f-test, is credited with the invention of the experiment. I should put it that way. Thorndike and Woodworth identified the need for control groups. Sir Austin Bradford Hill conducted the first clinical trial, and Jonas Salk used the clinical trial to test a polio vaccine. Okay. So again, let's talk through one more time that random selection versus random assignment piece. Random selection is how you draw the sample from the population. Random assignment is how you assign the sample that you draw to different groups or treatments in your study. Okay. So we can have a program group or a treatment group. Those are basically the same thing. And this is what you do in a comparative research design, like an experiment or quasi-experimental design. The program or treatment group receives the program of interest, and it's usually contrasted with either a no treatment comparison or control group, or a group receiving another treatment. Okay, so program group, treatment group, that's your X, they get the treatment. Your comparison group or control group is the blank, they don't get the treatment. They might be getting a comparison treatment, a different treatment, but they don't get the treatment of interest, okay, or the program of interest, or what have you. Okay. What does probabilistically equivalent mean? It's this notion that if two groups were measured infinitely many times, they would on average perform identically. Now, that doesn't mean that each time they'll obtain the same average score. It just means that over time they would come out to be the same if you just did that study again and again and again and again. Okay. So here is our design notation for a two-group experimental design. We have our randomization. One group gets the treatment and we post-test. We would typically look at this kind of test using a t-test for independent samples or an ANOVA. If you remember, you could use a one-way ANOVA for this as well. Or, of course, the non-parametric alternatives to these. So if you're doing this kind of study, here's all the threats that you might be facing. History, maturation, testing, instrumentation, mortality or attrition, regression to the mean, then selection, and then selection in combination with all of these except for selection mortality. And hopefully you're not also victim to these social types of threats. Okay. All right. So now let's talk about how we can take these designs a step further. We're going to talk about signal enhancing designs through factorial designs and noise reducing designs through covariance or blocking designs. So designs that focus on the program or treatment, its components, and its major dimensions, and enable you to determine whether the program has an effect, whether different subcomponents have an effect, and whether there are interactions in the effects caused by the subcomponents. Okay, so let's go through an example here. Okay, so here we have time in instruction 1 hour per week and 4 hours per week. And just to make this more similar to current times, we'll call this in-class synchronous and pull-out asynchronous. Okay. So as you can see, we have in randomized to these 4 groups. We have 1, 1, 1, 2, 2, 1, 2, 2. Okay. Now, how I think 1, 1 is obviously this one, and 2, 2 is obviously this one. 1, 2, and 2, 1 just depends on how you would have labeled these. So it doesn't really make a big difference as long as you know how you're keeping track of it. And here's our observations, of course. Okay. So let's look at the results for some 2x2 factorial designs. Okay. So in this case, you can see here, every group performed about the same way. Okay. So in terms of academic achievement, no differences. And that's reflected in the difference between asynchronous and synchronous and 1 hour and 4 hours. Okay, so now let's look at this one. Okay, so I see no differences between the synchronous and asynchronous, but I do see a difference between 1 hour and 4 hours per week. And that's reflected in the fact that 1 hour per week is down here, 4 hours per week is up here. But no difference, as you can see, between the asynchronous and synchronous, or pull out in in-class. Okay. Now we'll do the reverse. In this case, we do not have any difference between the 1 hour per week and the 4 hour per week, but we do have a difference between our pull-out asynchronous and our in-class synchronous. And you can see that here, or if you look at it this way, you can see it this way. Okay. Okay, so now what do we have? Okay, so this group does the worst, 1 hour per week asynchronous. These two groups, whether you're if you're in class for an hour or 4 hours per week with the asynchronous pull out, that's better. And then the best is in class with 4 hours a week in instruction. And that's how this would look. Okay, so notice there's a difference between both lines increase. Okay. Now let's look at an interaction. Well, the only group that's better here is this one. The only way to win is if you're in class and get 4 hours a week of instruction. So when we ask the question, is doing synchronous enough versus asynchronous? No. Is doing 4 hours versus 1 hour enough? No, you have to do both. And you see that reflected here. How do you know if you have an interaction? Graphically is the easiest way to know if your lines will cross at any point. If your lines will cross at any point, you have an interaction. Okay. Now, whether it's a significant interaction, that's where the statistics come in. But whether there's any kind of interaction out there, look if your lines will cross. Here is a crossover interaction in a 2x2 factorial design. Okay. So what's happening here? Well, it looks like the opposite effect is happening for each group. So in other words, if you're in class, 1 hour per week is no good, but 4 hours per week is really good. Whereas if you're asynchronous or pull out, the 1 hour per week works really good and the 4 hours per week does not. And you can see that's a true, you can see it's a true cross here. So that would be very interesting, because if you ask the question, okay, so is in class better? That depends. Sure, if you do it 4 hours a week. Okay, is 4 hours a week better? Well, that depends on whether it's in class or pull out. Okay. And so one other thing I want to point out with this is notice how the averages here are all the same. The averages here are all the same. So really, what makes the difference is within here, the interaction. If you just looked at the averages, you would say there's no effect. Okay. So what are some of the benefits and limitations of factorial designs? Well, the benefits are that they enhance the signal. It's an efficient design, and it's the only one that allows you to examine interactions. What's the limitation? It's complex. It can get really complex, especially if you have more than 2 different groups that you're looking at, more than 2 different variables. And more participants are required because you got to fill each cell. Right here, there were 4 cells, got to fill them all. Okay. So to show you what I mean, here's a factorial design with a 2x3. And we can see in this case, we're talking about different settings: inpatient, day treatment, and outpatient, and 2 different treatments, either psychotherapy or behavior modification. So if I look across here, there's no difference between psychotherapy and behavior modification. Those 2 came out the same. However, there is an important difference between inpatient, day treatment, and outpatient in terms of the severity of illness. And you can see that across these lines right here. Okay. No interaction for this one. This is a straight main effect. Okay, so now if you really want to get complicated, here's a 2x2x3. Same setup. Inpatient day treatment, outpatient psychotherapy, behavior modification. So what's different between this group and this group? It's the dosage. They're also getting a medication here, and the dosage up here is 100, and the dosage down here is 300. So as you might imagine, you have a lot of interactions to look at, okay? You can look at the interaction between the setting and the treatment. You can look at the interaction between the setting and the dosage, or you can look at the interaction between the treatment and the dosage. Or you can actually look at that three-way interaction of treatment by setting by dosage. So there's a lot to look at here. As you might imagine, you really need some good power, some good sample size in order to be able to look at this. And it also gets really complicated to try and understand what's really going on here. It can be done, but it's a challenge. Okay. There's also something known as an incomplete design within factorial designs. And once again, we have our inpatient, day treatment, outpatient, our psychotherapy and our behavior modification. And then we also have this no treatment control group over here. Okay. So now let's talk a little bit about some noise reducing designs, like a randomized block design. This helps minimize noise through the grouping of units into one or more classifications or blocks that account for some of the variability in the outcome. Okay, so what we're going to do here is we're going to block out groups that are the same and look at them separately. So here's one similar group. Here's a second one that's similar. Here's third, and here's fourth. These are not necessarily similar across each other, but within each group, they're pretty similar. Okay. A covariance design. This one helps minimize noise through the inclusion of one or more variables, such as a covariate that account for some of the variability in the outcome measure or dependent variable. So this one's probably more familiar. It's when you add covariates that you adjust for in your study. So most people tend to adjust for demographic variables in a study because they know that that can make a difference in the outcome. And this is a really cool thing. This is a hybrid design called a Solomon 4-group design. So in this case, 2 groups receive the treatment and 2 do not. 2 of the groups receive a pretest, 2 do not. And it can be viewed as almost a 2-by-2, but you're explicitly including testing as a factor in the design, so you can tell whether there is a testing threat occurring. So let's look at how this is set up a little bit. Randomize into 4 groups. We observe these 2 at pretest. We don't here. Why are we doing this? Because we want to know if there is a difference, if the actual giving of a pretest is going to impact our post-test. Then this group gets the experiment. This group gets the program or experimental condition. These 2 do not. So if I compare this group to this group, I can see, okay, if there's a difference between these 2, is it due to testing or is it a real effect? And then I can compare these 2 groups to these 2 groups that, that didn't get the program to see if there's an effect that way. So I can look at both testing and I can look at the effect of this, of the program. And so here is an example of this. Here we go. We have a treatment effect, but no testing effect. So here we have pre-post. Here we have pre-post. And as you can see, what happened is the one that got the treatment actually improved, but one that didn't get the treatment, there's really no difference here, right? So you can see here is at post, these two groups that got the treatment. Here is at post, these two groups that didn't get the treatment. Treatment effect, but no testing effect. Okay. Okay, so let's talk about a switching replications experimental design. Now, this is a two-group design in two phases defined by three ways of measurement. And basically what happens is the two groups switch roles. The original control group in phase 1 becomes the treatment group in phase 2, whereas the original treatment group acts as the control. So the way this works, again, you randomize into two groups, observe both groups. Now, this is the treatment group, right? You get the treatment, observe again both groups. Now you get the treatment, observe again both groups. Now this one's kind of interesting because you can have some different things happen. So here's one possibility with a short-term effect. Okay, so group 1 gets the treatment initially, see all that effect, and then nothing else happens because they're not getting the treatment between post 1 and post 2. This one doesn't get the treatment between pre and post 1, and you can see they even go down a little bit, and then between post 1 and post 2 they almost catch up. However, consider this. Now in this case we have the difference between pre and post 1, but what happens between post 1 and post 2? Well, like in the previous one, this one shoots up, but here, even though this red group is no longer getting the treatment, they're still showing not the same level of improvement, but still showing continued improvement. So that treatment had a long-term effect. Okay. All right. So what are some limitations of the experimental design? Well, you can have differential dropout, right? As we talked about before with our exercise program, exercise diet versus the pill. Ethical problems, all kind of ethical problems, right? Especially when one group's getting a treatment that you think will really work and the other group isn't. There are these social threats to internal validity, right? Especially when people in the non-experimental group find out about the experimental group. And most importantly, I'd say it can be difficult to generalize to the real world. You've set up so many controls, so many limits in terms of how the program goes, that how can we really imagine how this would actually apply to the real world? So that's one of the downsides of the experimental design. Okay, and we will talk through doing an activity when we are in class together. Okay, so we'll do an activity together when we meet, and that is all I have for you for right now. Be well, stay safe, and I look forward to talking to you soon.